Okay, so we're going to write down the density matrix generically. Now, of course, I'm going to use a two-level system so we can see the structure more easily. So the density operator in Hilbert space, then we have a two-level system basis. That's why I use an arrow. So rho AA of T, I'll use A and B for my two levels. Rho AB of T, rho BA, and rho BB. All right. Now, what do we know about the time evolution? We know the Liouville equation. So from that, we have rho dot is equal to minus I over h bar, h of t, rho of t. All right, well, we can put that in. So what we're going to do is we're going to look at the matrix elements of the Liouville equation. So we can write that by doing A. I'm picking one example, A, for example, the A element. A is minus I over h bar. A, and then we have here the commutator. H, I'll leave the t's out. We know that these all depend on time. All right, so we need to actually put something in here. So we have minus I over h bar, and then A. And now what's HA? So HA, or sorry, H rho. So H is all the matrix elements of H. Rho is all the matrix elements of rho. So let me do that over here. So we have HAA, HBAB, HBA, and HBB times rho. All right, this is H, this is rho, so we need to calculate the commutator, so it'll be this times this minus this times this. Okay, and then when you do that, what are we pulling out? We are pulling out the AA element of that. So that's going to be a matrix, right, with a lot of terms or several terms. And then we're going to take the upper left, which is the AA element. So I'm not going to work through multiplying these two matrices and then subtracting from the other. I'm just going to give the result. It's a worthwhile exercise, or if you don't like doing that at all, you can just plug it into Mathematica and have it do it for you symbolically. The answer that you'll get is this one. Remember, we're taking the upper left term, the AA element of this. All right, and so that's going to be a bunch of terms. So HAA, rho AA, plus HAB, rho BA, plus I over h bar. Do you see that minus the minus? That's where the plus comes from. Rho AA. Okay, the order of writing rho and A doesn't make any difference, but this is where it comes from the other backwards order. Plus rho AB, H, BA. You see a lot of symmetry here, right? AAAA, AAAA, ABBA, ABBA. If you saw something like ABBA and ABAB, you could guess that you made a typo somewhere. Those are good hints about that. All right, so what do we see here? We notice we have a plus I over h bar for rho AA, HAA over here, and a minus I over h bar AAAA, okay? So those terms cancel out. But these terms are different. This is HAB rho BA. This is HBA rho AB. So they're opposites of each other. So those terms survive. So we have minus I over h bar, HAB rho BA, minus HBA rho AB. All right, so this is telling us how, if we put it into language now, how the ground state population evolves as a function of time, right? Because that's what rho That's what the AA element of the rho will be. This is the time derivative of this. All right, so we're asking, okay, what is the time derivative of the ground state? So now you would have rho AA of t. You could then solve that differential equation. Of course, they're all going to be related to each other, so let's see what happens. The next one is very similar, rho BB, dot, of course. And I'm just going to write these answers down. You do it exactly the same way. Just look, now we're looking at the BB element, so it'll be the bottom right element, minus I over h bar. As you can imagine, there'll be a lot of symmetry. You can almost just swap all the letters. Rho AB. I think you can, in fact, exactly swap all the letters. HAB, rho BA. Voila. Okay, so that's how the excited state population evolves. Well, it's how its differential equation is written down. Then we have the AB element. Right? So this is quite different from a wave function picture. Now we're looking at the equation of motion for the coherence, the AB coherence. All right, let's see what influences that. What you're going to see, this is going to look like a rate kinetics model. Right? Of course, there's going to be a I in the differential equation, so there'll be some oscillatory things. But you can think of each point in this system as a kind of like a rate constant. Okay, so here we have okay, minus I over h bar. Then we have HAA minus HBB times rho AB plus HAB times rho BB minus rho AA. This is kind of interesting, right? You can interpret these numbers already. HAA minus HBB, that's the difference in energy between the two states, the diagonal elements. This one is the difference in population between the two states. With the coupling, and this is the difference in the energy with the coherence. Yeah, so you can actually start to think of these like in intuitive ways. All right, this one is the other way. Because it's a complex conjugate of it, it should be relatively easy to figure out. We just need to either put a plus sign here, or we can write that if we like to keep all of the minus signs the same, which we do because we want to combine these in a minute, then we'll write it like this. HBB minus HAA, so just the negative of the one that you have above, with the other coherence, HBA, and then it's going to be the other direction of the, what sometimes in physics they call the inversion, the difference between the two states. Since you have normalization in a two-level system, you don't really need to separately store the ground state and the excited state population. You could just store the difference between them because you know, of course, they add up to 1. Okay, so now we've set the stage, set the table, so to speak. And what we want to do now is do something that's like one of these amazing sleight of hand tricks that I think somebody who was very good at math and science figured out before us. All right, and the idea is very simple. We have these 4 elements, or 4 vector components, or sorry, 4 matrix elements components. Remember, it's AA, these different components that we're considering. And then, as I hinted, at least in one of our discussions, was imagine that you write the matrix and store it in a slightly different way. Imagine that you write this thing, okay, but then you connect these by a piece of string. And you connect this one by a piece of string to that one, and then you connect this by a piece of string to that one. If you do that, then you can imagine pulling on the ends of the string, and the thing that you stored in a square because that made sense to you because you thought of the density operator as an operator in Hilbert space, there's nothing wrong with pulling it out and thinking of this as 4 components of a vector. And that's exactly what we're going to do now. So we're going to get ourselves a little box so we can write stuff. I think it'll fit. So we already have all the terms here, right? This is rho AA dot. This is rho BB dot. This is row AB dot. This is row BA dot. So we're going to write them over here. Row AA dot, row BB. Now the order that in which you write them makes no difference, but you have to make sure you do it right the same way every time. And so that means I have to look at my notes to do that. All right, good. And then row BA. And this is a vector now. We're going to think of this like a vector. Okay, fine. Then on the right-hand side, we have minus I, oops, we need an equals. Equals minus I over h bar. I'm trying to make that fit as easily as I can. Okay, now, it's not something that you can easily probably do in real time, but it's something that has been done. It's been done by other textbook authors. It's been done by me, and I know it works. So I'm going to simply write the result. If you're interested in trying to figure it out for yourself, that's no problem. We know what the vector is going to be. Right? The vector is going to be these things without the dots. Row AA of t, row BB of t. This is what a normal differential equation looks like. So you just go and remember all the t's are, not shown here because it would have taken another board to do it that way. So you can go and look through. You can say, oh yeah, I'm going to need to multiply HAB by BA to get a term that I need in this equation. I'm going to need to do HBA times AB, which is here. So when you do that, you can identify all the terms in this matrix. Now, how many terms are there going to be? 4 by 4. Okay. Now, fortunately, the way I've packed it up here, the upper 4 are zeros. Obviously, there's not every term here, so you expect, some simplification. Okay, then what we get if we follow it all through is minus HBA plus HAB, so positive, HBA minus HAB. All right, then down here we have minus HAB, HAB, HBA, minus HBA. Then we have 0 here and 0 here, and then these guys we have two terms that are combined. This is the difference in the Hamiltonian diagonal. So HAA minus HBB. Oh boy, this is bad. And this is the other one around. HBB minus HAA. Here's what I'll do. I'll put a box here and draw it up there. This term is HBA. So no, HBB minus HAA. All right, and this is the other one. Okay, so all we did was write down the Liouville equation, Liouville-von Neumann equation, which is here, which we derived earlier in the course. We write it into level system. We see that we can write each element of the density operator and what its time dependence is, or what its time equation of motion is. We then realize, okay, our density operator has 4 terms in it. We can store them in a square, or we can store them in a line. It makes no difference. But there's insight if you store them like this, because if you stretch them out and make it into a vector of these time derivatives, then you end up with an equation that looks like this. It looks like a big matrix times the vector that's over here. Okay? And in fact, what you can do is you can summarize this whole giant equation with this relatively simple notation using the summation notation like this. So the jkth element, and everything depends on time, so we're just not drawing the times, is minus I over h bar times h rho jk minus rho h jk. All right, and so this is the matrix version, and this is the vector version of exactly the same information. All right, and so there's a whole bunch of different things you can do here. One of the things that you can do is you can ask yourself, why on earth would you do this? This seems worse. This seems like we made anti-progress because we took something that was a vector, a matrix, we turned a vector, but we ended up now with a new operator that's out in front that seems to have n squared terms in it. That seems worse. But it's all exactly the same information as that's encoded over here. It's just packaged in a different way. There's nothing different about that from this point of view. But what is very important is that there is a way that we can think about all of this. So let me clear off a bit of space and introduce some terminology that will be very powerful. All right, so what you see clearly, what we've done is we've transformed by nothing other than essentially bookkeeping the density matrix into a density vector. Okay, and so what we can do then is we can introduce an operator, this one here. Now, we can choose this operator. Certainly this operator is a matrix, so it has ij elements or jk elements or whatever. Or we can choose to have this matrix represented with four indices. Why? Because we have each location in here is connecting each of the four different pairs, density matrix elements here, right? So we could have an AAAA element, that would be this one. We could have the AABB element, which would be this one, this one, and so on, all right? So we can write down rho JK, but now thinking of rho JK as this one of these elements of the vector, just that we use two labels to tell us where we are in the vector. If you don't like that, you don't have to have that. You can have rho n dot, and then this could be 1, 2, 3, 4, as long as you keep track of it. All right, so we're going to write this in minus I over h bar as usual, and then we simply sum over m and n, the sort of internal labels, a new operator, which I'm going to use the script L for, and this has elements j, k, m, n, and we multiply that by rho m, n. And we'll be summing over m and n. When you do this, you can convince yourself that this gives you the same thing as this. This operator, this matrix here, becomes the matrix L. And this is just the way we multiply matrices by vectors, with the little, I guess, caveat, which is to say this is just, we're labeling the locations in vector, locations in a matrix, with two indices instead of simply one. Okay, so what is the point of all of this? The point of all of this is that we have transformed our previous sort of formulation of quantum mechanics, right? Which is that we had, for example, Cj dot equals minus I over h bar sum on m h jm cm. This is just our normal Schrodinger equation. This is the Schrodinger equation, and this is actually the Liouville equation. Just repackaged. It's really that simple. It's repackaged. We didn't add any new physics here at all. Physics will come later. This is really just another sort of picture. The way we had a Schrodinger picture, or we had a Heisenberg picture, interaction picture, or in classical mechanics, when you think about being governed by Newton's law. Certainly that's fine if you prefer to think about things in terms of forces. But you also can write down the Hamilton's equations, which are in terms of the energy, the Hamiltonian. Classical position and momentum, various derivatives give you another set of equations called the Hamilton's equations. Maybe you saw that in statistical mechanics, or we took a class in classical mechanics and physics. Then you might have seen that formalism. And of course, they're equivalent things. There's nothing about nature that cares whether a physicist is describing the motion of planets or bumblebees or flocks of birds with a Newton's law or with Hamilton's equations. It makes no difference. But there are some things that follow a little bit more easily when you use one versus the other. And especially with Hamilton's equations, you see lots of things that remind you of quantum mechanics, especially if you knew quantum mechanics better first, like actually probably a lot of chemists do. They probably don't learn quantum mechanics very seriously, classical mechanics very seriously, until they see quantum mechanics, and then maybe they go back and they have a little bit more of an intuition about that. Okay, so what's going on here? We are going to, this is an equation or a system that we think about it as being in Hilbert space. In Hilbert space, the vectors are like things like the state of the system, and the operators are matrices. In the case of Liouville space, we are going to have the system is going to be represented by the density. Rather than being an operator, the density operator will appear as a vector. So it's the lowest sort of level thing that you have in Liouville space. And then the operators are represented by what are called superoperators. Sounds good, right? They're Liouville space superoperators. Sometimes they're called tetradic or tetradic notation, which is referring to the 4 labels here. All right, and so we're going to develop the entire linear algebra of Liouville space, inventing or using some notation that will look just like the Dirac notation for Hilbert space. We will have Liouville space vectors, Liouville space operators, trace, scalar products, you name it. And that'll allow us then to formulate all of our equations of motion in Liouville space, and then we will derive the Dyson series in Liouville space. We will derive the time-dependent Schrödinger, time-dependent perturbation theory in Liouville space, and then we will use that to derive the optical response functions.